John Jones is with the University of Illinois, and he's going to, he's associate professor, or I'm sorry, so assistant professor. I just gave you a promotion. What the hell? Assistant professor of agronomy and soil fertility extension specialist at the University of Illinois. Thank you very much for coming.
Great. Thanks, Bruce. Thanks for the invitation to come up and speak. I really enjoy seeing a lot of familiar faces in the room. Story about Sotab in the back. We roomed together in grad school at all the ASA meetings, so it's always fun to see people that you never would expect when you run up here. Again, thanks for the opportunity to talk. So a little bit of disjointed topics, maybe when you look at my title. So I'm now at the University of Illinois. I've been there for about a whole 6 months, but I was at UW-Madison previously, which I'll share some of the work where I did research to update soil test P&K interpretations for Wisconsin, and then I'll also show some water quality phosphorus data that we did in Iowa for my graduate work. So I'll kind of was asked to kind of bracket the state of Minnesota on some of the research that we've done there. So that'll be the topics that I'll share, and you can see this here. So in the Wisconsin research, it's really agronomic focused. So I'll talk about field correlating and calibrating soil test phosphorus. There were P&K efforts at the same time, but I'll just talk about the phosphorus data today, obviously. And that work happened from 2021 when I arrived at Wisconsin until actually finishing through last year, and there'll be one more year of data on those studies. In Iowa, I'll summarize some of the work that I did under the advisement of Dr. Antonio Mallarino in collaboration with Dr. Hawk and Dr. Helmers at Iowa State, really kind of taking a 4R assessment to phosphorus loss, but certainly looking in the context of agronomic production performance as well. Setting the stage for phosphorus use and phosphorus work. So this is a table showing the median soil tests P and also showing K. For the North Central region, in the most recent soil test summary that was done, started by the International Plant Nutrition Institute. I helped lead that in 2020, and actually with some alumni of U of M and myself, we're going to be leading it in 2025 as well. This just aggregates soil test data by state that's volunteered to be submitted by the soil testing labs. The most recent survey was around 9 million soil samples around the U.S. This is just for the North Central region that you're seeing here. And if we kind of bracket Wisconsin and Iowa, two different scenarios, and these trends hold pretty steadily from what we've seen in the most recent summaries as well. Certainly big challenges that are kind of separate when you look at managing phosphorus in different states. Although there's really a history of manure in both states, we have certain differences in amount of cropland, the density of livestock, and things like that have probably played a little bit more role in Wisconsin phosphorus management historically, and we've seen these trends decrease in soil test level. For Iowa, not much change. And Iowa, I can tell you, has the most soil samples in this database. It's over 1 million soil samples, at least in 2020, and a little more consistent, and probably those tighter rotations might affect that as well. Soil fertility concept to build upon. So this is what I'll be really talking about today, and kind of the main concept of data that I'll be showing as well. So certainly as we move from soil test levels on the left, going from low to very high or the opposite direction, we have different supplied amounts from the soil, and then we're trying to make that up from fertilizer. How do we get to that point? I know Jason talked about and Javed talked about the process in their states of doing this, and I'll discuss that as well. Certainly one thing that was discussed already, and it's important to look at, is just the probability of yield response as this changes. Can we implicitly define that? That really doesn't happen very often, I think. So the research efforts that I'll talk about, and again, I'll go through the Wisconsin work first, to refine soil test phosphorus interpretation really took about 3 steps. So the first was to field correlate, and I know Jason showed some really great graphs that step through this process. So this is actually a nice sequence of talks, I think. The first step was field correlating soil test levels to crop fertilization response using relative yield. Not absolute grain yield, but relative yield, because unlike when we're working with nitrogen recommendations and optimum N rates, we don't just have N rate and yield. We have soil P level, our control yield, and our fertilized yield. So we need to have that response to fertilization as a response variable. Identify ranges of soil test values that we can interpret at least in a similar fashion. Within ranges of those empirical soil test units, and then calibrate those tests for rate responsiveness and across different lows, highs, and optimums, and I'll share a little bit of that. All this requires a lot of work. Thousands of soil samples every fall, every spring, hundreds of plots run every year, and it really takes hundreds of site years of data, I think, and a lot of multi-year evaluations to really start to see when this data takes the shape of something that we can start to interpret. I'd like to just give a little bit of a background on the Wisconsin philosophy for the rate recommendations, because it is different and kind of baked into a lot of specific states around the North Central region. Wisconsin has a hybrid sufficiency and build approach. What you see there in the bars is essentially what makes up the rate recommendation. So it certainly decreases as we increase soil test category, but really it's broken into a build component and a removal component. And if you actually calculate build from wherever your soil test level is to your target, and then your removal for your intended yield, that should get you almost exactly of what the recommended rate would be in the tables for the recommendations. What's a little bit different depending on the state you're at is the recommendation above the optimum level where it's just crop removal. So Wisconsin uses half and then quarter crop removal rate recommended rates for potassium only for the high soil test category. There is no phosphorus recommended in the very high or excessively high categories. That quarter removal rate isn't there. And then it assumes a build, if you just run the numbers, it's 6 years, but 4 to 8 years. So when you look at that, and this is a potassium example, but it'd be the same for phosphorus, depending on your crop and your removal amounts, the components that make up that rate recommendation will change. And so it's important when we think about the build or removal components, how accurately our science is really identifying what those really are. So if you look at the green bars or the bars on the bottom, those would be the crop removal component of the rate recommendation. This is for corn grain on the left, corn silage on the right. It's a nice comparison because you see how removal of corn silage is affecting this K recommendation. So I just wanted to show this because this is kind of baked into a lot of the system of how the data is interpreted. So the studies that I did when I was in Wisconsin were, again, P&K calibration studies. It might be a little hard to pick out the red and green stars on the map there. The red sites were our field response studies were done around the state. And usually for a given location, we had multiple sites, research sites or trials at those given locations in different fields and on-farm and on-station work. There was corn, soybeans, and corn silage done each year. I'll only talk about the corn and soybean grain data. If you have any questions on the silage data, I can be happy to send that. We did have some tillage comparisons. So for 3 sites, we had no-till and tilled sites that we could compare. Most everything was conventionally tilled. So chisel plow in the fall, cultivator, soil finisher in the spring. As you can see across the color gradient across the state of Wisconsin, quite a wide range in soil texture, pH. If at least what we were starting at with an inherent pH, usually we wouldn't let things drop below 6.5 if we were running P&K studies on them. These were full factorial P&K treatments. I'll show one slide that shows a P by K interaction, but really won't get into that too much today. But we could look at that. And really the biggest need was to calibrate more soil tests. So at this time, the Bray 1 phosphorus and potassium test are the only calibrated tests in Wisconsin. We don't have data for the Malick. We didn't end up using the Olson or H3A, but that was in the data set as well. This is all 6-inch sample depth, and every test was independently calibrated. And I'll kind of bang on that drum as long as I have to, that we need to calibrate each test independently and not auto-regress them between each other. And that's just an aerial image of one of the studies. Overwhelmingly, the potassium deficiencies are what popped up more than phosphorus for these studies. I said I'd show one interaction slide. So this is just from a 2-year time span in the southern Wisconsin sites. This is yield response to soil test ranges of phosphorus and potassium. So if you go on, it's corn on the left, soybean on the right. As you go from the 3 bars from the red, gray to blue, or the 3 bars in order, you go from a low phosphorus range to a middle or optimum range into a high soil testing range. And then as you go in groups of bars across the screen, you'll see a different soil test potassium ranges. So we did see statistical interactions between P and K levels. Now I want to kind of warn against saying that these are internal metabolic interactions between P and K. I think what you're just seeing are meeting different thresholds of nutrients. I don't really consider these a true physiological interaction. I think it's more of a statistical exercise that we're meeting different thresholds of phosphorus and potassium. And then my final point before I kind of get into more of the meat and potatoes of the data, and this is a K example, but we see the same trends for P, is that this really requires a long-term approach. Running in and doing kind of 1-year strip trials for P and K are nice, but we really need to look at long-term trends and changes. There questions earlier about buffering capacities and soil test changes over time with removal. We need to track those things. And that's where kind of having a long-term mindset for a lot of these studies, I think, really helps and adds value. So can I take this off? All right. Kind of a wanderer, sorry. So what this graph is showing, and the question you kind of always get, and I think was important before getting into some more of the information and how I interpreted the data, is should soybeans and corn have different soil test interpretations? From my data, at least in experience in Iowa and Wisconsin, no, we didn't see any differences for soil test interpretation levels. That's not necessarily looking at rate, that's just looking at how we interpret and categorize soil test levels. So within this, but one of the things I think that's really important. So in the graph, you see red dots for corn, green dots for soybean. And we really we couldn't split apart the data to say one had a critical level of this and one had a critical level of that. When you used a relative yield equation and put them together, we saw similar interpretation power. But what does need to happen is you need to have corn and soybean grown in the same year. I'm really adamant about that because we see annual effects of yield potential of that corn and soybean. And I'll show an example on the next slide for K response specifically. We don't see it as much for P, but we see really big differences in optimum K rates when we have different dry, essentially precipitation conditions. So that's one of the things that is kind of a theme throughout the data that I'll show is I'll put corn and soybean together for interpretation. We're not splitting them apart, and this is kind of the background for why I did that. But we do see really big differences in terms of rate responses. So what this is showing are soybean yield responses to potassium fertilizer rate. The black points, or the graph on the top, is when we had within 5 inches of rainfall of a 30-year average for the site. This is I think there were 16 site years, split 14 and 4. The lower curve, where you're seeing kind of a flat line with your lower yield potential, is when you essentially had dry years. So you had less than 5 inches of rain within the 30-year average, essentially. So you're in drier conditions, lower yield potential. Now our optimum K rate really wasn't entirely that different, 108 pounds on the upper curve and 90 pounds on the bottom curve, but certainly a difference in terms of what we would expect our removal rates to be in this case. So what was going to be replenished after this crop is certainly something that's affected by weather and yield potential as well. So I'll kind of hop into some calibration, or excuse me, some field correlation data looking at how we broke out the yield response. So this graph shows relative yield, again, corn and soybean together, of the two main ways that Wisconsin breaks apart soils and sites into loamy and sandy categories. So loamy sands kick over to the sandy category, sandy loams kick over to the loamy category. If you want to interpret how to work through that, be my guest. It's very challenging. I would say the thing that gave me the most headaches working in Wisconsin was how to manage P and K correctly, or what is the correct way on sandy soils. But this is how it broke out. So within the sandy category, there are irrigated and non-irrigated coarse textured soils. Something that was a little less important for P, but more important for potassium. And you can see that the lion's share of the data is within those loamy sites. And that kind of is a maybe inverse L from the northeastern part of the state, hooks around and it represents the bottom half of Wisconsin as well. And so within this, we see some trends and patterns that maybe aren't necessarily really surprising. When we saw an increase of relative yield as we increase soil test level, I'll mostly show Bray data when I'm showing graphs and figures. But again, in the tables, I'll show some Mehlich 3 data as well, because that was calibrated through the same process. And so when we look at the critical levels, and I'll show them in a table here with some actual numbers, certainly we saw differences between our coarse and fine textured soils. One of the things that I did end up changing when looking at interpretations was widening the optimum range. Before it was about 4 parts per million. And I just thought that was a little too tight of a target to aim for when looking at the variability of soil testing that Craig talked about earlier, that we do know we have, depending on how you're pulling samples, what labs are being used, and things like that. I just thought widening that optimum category would make a lot of sense. For the sandy soils, we really didn't change a whole lot. We moved some of the interpretations up. And one of the important things about so you can see as we move from very low, low, optimum, high, and excessively high, one of the ways that these ranges are broken out is by identifying levels of responsiveness, or probabilities of site response to P in this case. And I'll actually blow up that bar chart on the right there, but those are the probabilities of response levels for each class. And the reason they're broke out like this is how it was clearly defined in the UW recommendation document. So the numbers and ranges of rate responsiveness are something that are defined as empirical numbers. And so we wanted to keep consistent with that, because in terms of growers and agronomists interpreting what is a very low, what is an excessively high mean, we wanted to make sure that their consideration and anticipation of a P fertilizer response was consistent over the last 40 years of the document. And so that's how these got broken out as well. There's some other statistical kind of tricks to look at things like the error associated with all these responses, but that's also what was considered. So this is the table for the new interpretation classes. Again, we'll have another year's worth of data that goes into this, but generally I don't expect those to change a whole lot. And I'm sorry, this is kind of hard to see on the bottom, but those are the older categories, and they shifted a little bit to the right or up in terms of an increase within that optimum range, and it kind of drug the low, optimum, and high up. But one thing that really didn't change was that kind of a excessively high border, or where we would start to consider higher testing P soils. Now, what level of P soils are we really concerned with for water quality issues? Probably not all. I mean, we and I'll show later, we see measurable P loss from optimum soils still, but it's those 90, 100, 150 parts per million soils that we're most concerned about when thinking about hotspots for phosphorus loss. And so for within these categories, we weren't necessarily concerned about adjusting things to a higher optimum range in relation to water quality. Now I said the Bray P1 test was provided before in terms of calibration for the state. The Malick 3 colorimetric data is here as well, and the Malick 3 ICP. The ICP number should be higher as it's measuring, we assume, some pools of phosphorus beyond orthophosphate or mineral phosphate. We don't always know exactly what forms those are, but we know it's going to be a higher value. And so these numbers are what I ended up coming at for the loamy and sandy categories. Now, when we take a look at this and kind of throw some examples for economics to it, I think that really is important, because when we think about this as an agronomic exercise looking at yield response, we don't consider profitability and returns in that nature. So what we've done within this data set is kind of pull it apart and look at net returns to phosphorus, because we had fertilized treatments in all these studies across soil test levels. And so what we did essentially was, this is really kind of an inverse of that yield response. This is looking at net returns to phosphorus fertilizer based off of soil test levels. So you would expect them to be higher when you're at your lower soil test P levels. Sorry, I still have pounds per acre there. I apologize. I'm in Illinois now, and so we have to communicate things on pounds per acre. So my slides are going back and forth. Divide by 2, and you'll be at parts per million. That was a big transition for me going south, but. So I apologize for that, but I'll show kind of some numbers that are important here. So one of the things that these figures are showing are a consistent fertilizer price, so about 75 cents per pound of P2O5, but essentially moving from less favorable to more favorable price conditions for crops. So really, in reality, we're kind of bouncing between these two areas where we're at 450, maybe lower, maybe higher corn, and a little bit higher soybeans, but these are some ranges that I used. But what I think is important with this point is to look at these break-even points where we do crash and hit 0 for our net returns to phosphorus fertilizer. Really, those should be about what our critical level ranges are. Now we can argue, should it be the higher end of that range and the lower end? Probably the lower end, or the higher end, because that's where we assume everything in the optimum we manage the same. But essentially what I wanted to look at was, does that break-even point of economic response to phosphorus fertilization, does that match about what we found for a critical level or optimum range? And if you reflect back, our optimum range, the upper end was about 24 parts per million for the Bray test. And so this ended up being a little bit higher, even with what I would say less favorable crop conditions. But and maybe these higher price scenarios get a little bit higher in terms of where the break even meets. But what I would consider where we're at now, this is pretty darn close to our 24 parts per million in terms of a profitable place to say we should probably cut off or really reduce our phosphorus fertilizer rates. When you look at these graphs, so the dark points are corn and the light points are soybeans. One thing that I would take away from this, though, is not to chase soil test levels based off of economics. I don't think that's a good decision to do, because you're going to be wildly chasing and running your tail all over the board trying to say, well, what's my soil test level this year? What are prices this year? What do I need to get at to? What's my buffering capacity? What's my drawdown or buildup rates? I think you'd go crazy trying to do that. I think a rate discussion of what are our current price conditions makes more sense, but not chasing soil test levels. Now, if we do the same exercise and look at a consistent price of corn and soybeans and look at a changing price in fertilizer, so going from relatively cheap phosphorus at 65 cents per pound up to 85 cents per pound, so kind of brackets what we're looking at now, and I think we're a little more closer in terms of our, let's say, DAP price to 780 per ton. I think we're a little bit lower than that now. But essentially, this is how that data looks as well. So certainly when we go to a less favorable pricing scenario, all these points start to condense, right? Because we have a lower flexibility or less flexibility to make returns. Margins are tighter. And where we're at now, again, was about, and this is the same combination of prices almost as what you saw earlier, where we're at now is about that 24 parts per million of P as kind of that upper end of the optimum range. Exactly what the agronomics showed as well. So this was really, I would say, supportive of the process of looking at relative yield and interpretation to look at data in terms of an economic response. And again, I would say through variable fertilizer pricing and scenarios, maintaining those optimum levels has a lot of benefits, and I'll show some more a little bit later on to buffer those tough times as well. Now, I said I'd blow up this figure and talk about it a little bit later. So this is the probability of response that was assigned to each category. So we're going from very low to low, optimum, high, and excessively high. So Wisconsin for P shoots up to excessively high. And one thing I wanted to show was K in this case as well, because a lot of these soils and sites were a lot more responsive to K when we looked at them. And in general, K nutrition was probably a bigger challenge for me as a researcher in the state than phosphorus really was in terms of trying to understand why we saw responses when we shouldn't have expected to. And so just a picture of some fairly consistent soybean K deficiency symptoms that we saw throughout the studies. But these numbers I think are really important to define because this is what we should expect as agronomists and as farmers. This is what we should say and these are a little bit higher than some states. I know Iowa uses 85, 65, and 25 or something like that when going from very low to optimum. But these were defined by the state already. And we wanted to stay consistent with that. And kind of a story behind that. So this is the official UW recommendation document that's being updated right now, but has the probabilities of response over here. So they're actually very defined specifically, and this is what we wanted to stay consistent with because coffee shop talk, well, I've got a high testing soil. What does that mean? Well, we can really define what it means. And so that's why we stayed consistent there. Now, if anyone goes back to their what graph I showed earlier, a figure I showed earlier in the slides to their John Havlin soil fertility textbook, you've noticed that these numbers are actually the same as what we see in the Havlin textbook. I don't know, and it's just a chicken and the egg of which came first, but it's interesting that that these actually matched pretty closely what or exactly essentially what we had in these scenarios within the UW recommendation. So I think this is important to talk about though and really well defined because again, this is in terms of kind of human communication, the social science of it all, what do we expect a high testing soil is? We know what numbers it can be, but what does that mean for probability of response? So now I'll get into the calibration part of the work. And so the field calibration work that was done essentially was looking at different phosphorus rates across soil test levels. And some of it seemed fairly textbook when we started to break out these figures. So this is around 50. So it's a fewer number of site years because we only had a limited space to do the actual rate responses here across these soil test levels. But essentially, as you're moving from these lower lines to these higher lines, you're moving from a low testing soil to a high testing soil. And the orange triangles are the optimum P rate that was met through the modeling effort and fitting curves to the real data that was behind it. You'll see these numbers there in the bottom of the graph as well. And so for this, we split out corn and soybeans, right? Because we're looking at a yield response to fertilization, and we're not going to use a relative yield scenario here, and I'll show why I did that before. But not surprisingly, we saw a higher and higher magnitude of response when we were starting on at lower testing soils. Now, one thing that's important within all of this is not the same method of the way we looked at building rates before. This isn't looking at building to a certain level and then applying removal. This is just at what soil test level do we optimize yield and profitability. This is not considering build at all. So it's more of a sufficiency approach when looking at what P do we need to supply to that given crop. If you added your build numbers on there, they'd certainly be higher than this. And this is how this data, the same data that I just showed in the graphs, looks when we break it out into a table. So you've got corn on the left, soybean on the right, those same soil test P interpretation classes from very low, low, optimum, high, all the way up to very high where we would not expect a response. Kind of these similar pricing scenarios, so a little bit higher than we're at now, but 75 cents per pound of P, $5 corn and $12 beans. Again, these were those optimum rates and these were the yield levels at those rates that were identified. And these were the net returns at those levels. And one thing that I think is important, and I think we kind of all see this when we look at corn versus soybean response to phosphorus, is that the phosphorus data is just a little more muddy. And I think what Jason talked about with mycorrhizal fungi playing a role is what I think we always talked about in terms of muddying the water as well, and some of the at least soybean response and what we thought was happening. But you can see when we get to even these optimum and high testing categories, for really both crops, but mostly soybeans, we're getting to the point where we're crashing near zero. And if you remember that cloud of data of net returns to P, that was a pretty wide range. There's no ranges here. I just have single values. But we have to realize that there certainly is a lot of variability. We saw a lot of non-responsive sites in the low testing categories. We saw a lot of responsive sites. Maybe I shouldn't say a lot. We saw some responsive sites in the high testing categories. So even though there's one value up here, these are messy systems, I think, and certainly shouldn't always be taken as clear cut. One question that I got kind of when working through this data is, all right, so do these yield levels match what I'm seeing on my farm? Are these profitable yield levels? Are they 25 bushel beans and 160 bushel corn? That doesn't match what I'm getting on maybe my farm at home. And so what I wanted to do was share, this was the non-limited range of yield. So this would be when we're calculating relative yield, the denominator or the non-limiting yields that we used in most of the studies, or found in most of the studies. So when you look at these ranges in the LOMI categories where I said most of the data, some years 197 was our non-limiting yield. Some years it was 273. So a big range, but certainly when we look at these ranges of corn yields and soybean yields, I would say they're profitable crops. And so I think this is kind of important to just define. This is all baked into the background of, and the foundation of a lot of the recommendation work is what were the non-limited yields and were these necessarily, do they represent profitable systems on a regular farm out in the countryside? And I think they were. So I'll talk with a few kind of concepts related to this work and then move into the water quality, a few slides to end the talk. One of the things that I think is important to remember, and this is just from 21 and 22 data, but we're cycling nutrients through our soils a lot faster and at high velocities than we'd ever done before. And it's really driven by yield increases in removals. But even if we're just applying removal rate and we can optimize at least stay within the optimum category, the amount we're removing and the amount we're having to replace are larger amounts over time because of higher yield levels. And so we're having to cycle nutrients through these systems. And within that, our predictive power is maybe sometimes a little bit less. Now, certainly while all this is occurring, and this is that same data set from the same site years, we do see some trends maybe in grain nutrient concentrations as our yields go from a low ranges to high ranges. Now, I put lines on here, but don't look into these patterns really too much. But we've known as removal rates and removal numbers per bushels get updated around different parts of the Midwest, that usually they're decreasing. Now you've got kind of an anomaly with K in grain there, and you could say that's kind of a loosely fit line. I think there's something else there, but for phosphorus levels, I think this kind of shotgun spread is what a lot of people have seen. A few notes from this work that I think are important. I talked about the H3A test earlier, so I'd be remiss if I talked about it here. This is actually Iowa data from that we worked on during my grad degree there. This is just showing the amount of sites above and below what we identified as the critical level. For the Bray test on the left, 54% below, 46% above. And for the H3A test, about not too dissimilar. We were able to look at curves, similar patterns. But when we started using things like phosphorus mineralization factors and trying to estimate what that either P solubility or biological activity was doing, it really muddied up the water and made the predictive ability worse. And so this is the same Bray test on the left. This is plus using a mineralization factor that some labs have been using. And you can see that we really just kind of overestimated the amount of P that's there. So I would caution against that and just consider what's really mechanistic and where do the statistics hold up. So one of the questions I also got was a comparison of the tilled and no-tilled sites. And within the data set, I said we had three locations where we were able to pull this apart within the 4 years. What we saw was no difference in terms of soil test depth for performance within the tillage system. So you've got chisel plow and a conventional till system and spring cultivation or disking on the upper range, no-till on the bottom range. Now we see some stratification. We know that's present. These are soil samples either in the top 3 inches, 3 to 6 inch, or the full 6-inch depth. And we really didn't see any difference in terms of one depth being able to predict better, but I would say that the models fit a little bit cleaner and the interpretation made more sense for 0 to 6-inch depth. So I don't necessarily buy that we need to be changing our soil sampling strategy for every distinct level of stratification. We know it exists, but we know our crops can get to and kind of experience high nutrient concentrations in the soil at different depths as well. And one of the things that from that data that did pop out, though, was that we did have more variability in specifically the no-till corn response to phosphorus. So this is really just a measure of relative variability of the process of fitting the yield response. And you can see that the blue box here in the corn was a little more variable, and that was pretty consistent throughout the whole data set. So our no-till corn response to P was just a little bit higher. Now, connecting this to kind of agronomic performance to nutrient stewardship for phosphorus. So what I wanted to share was some results from a study, and 2 specific studies, I guess, we did in Iowa during my graduate work there. The first one, and I would guess that maybe Antonio shared some data from this study at some point. It's maybe the older one, the older phase of it in Minnesota at some point. But essentially, this was a 6-year study done in Northwest Iowa. Essentially, this was a continuously monitored surface runoff study where we had different phosphorus fertilizer placement and placement and timing strategies in a conventionally tilled system versus a no-till system. There was a high soil test P treatment that we did have a cover crop in that I'll talk a little bit about, where there was no P applied. It had a history of a nitrogen rate-based manure program. We measured soluble, bioavailable, which is using an iron oxide strip, and total P throughout the whole system, and soil loss as well. And these plots were really designed initially to be useful for soil, the universal or revised universal soil loss equation estimates that were done by NRCS in the state of Iowa. I'll just again show things throughout the 6 years that I worked on the project and it got finished up. These are the yields from those systems. So as we're moving from a conventional tilled system on the left, so as banded phosphorus, broadcast phosphorus, no-till banded versus broadcast phosphorus. One of the important things is this no-till cover crop system has no P applied. It was already a very high testing soil. So this is just a comparison across all years and the averages of the yield response data. We did see some differences within the years, but in general, things were kind of a wash. For soybean yield, we didn't see any statistical differences there, though you can say that there's a little dip with your no-till cover crop system. Really for corn, we just saw an effect of the tillage. We didn't see any effect of P placement, and I think that, or timing, and I think that matches what Dr. Malorino had seen on the agronomic trials that were done around the state as well. This is kind of the take-home slide for P and soil loss. So as you move from the upper left and kind of circle around in a clockwise fashion, we have soil loss in tons per acre for the 5 systems, total phosphorus loss, particulate phosphorus, and soluble or dissolved phosphorus loss. That particulate P is really just calculated as a difference between dissolved and total P as well. So important kind of consideration to take place. But one thing I think is kind of a take home is that when we look at our total P values, these really only range from about 1.5 to 3.5 pounds of P2O5 per acre, per acre, across these 6 years of the study, right? So these are not necessarily annual averages. And so, or excuse me, these are annual averages. So when you would take that times 6 across the 6 years of the study. And so when we look at these numbers, they're really a small fraction of our phosphorus rates that were applied. Now the rates were applied at either 50 or 100 pounds of P2O5, and I'll show the rate effect in a little bit here. But really when we looked at the system's performance, some things were a little bit muddy and some things came clear. So there were clear advantages to a reduced till system when we looked at the amount of soil loss. So as you move from the broadcast treatments on the left, the chisel and no-till system, over to the banded treatments on the right, and then we have that no-till cover crop treatment as well. We certainly saw a larger amount of total P loss when we had a tilled system where we were broadcast applying P. And a lot of that came in a particulate or sediment-bound P form. We did reduce our total P when we weren't applying phosphorus, even in a high testing soil. This was with a cereal rye cover crop every year. One thing that we certainly looked at was the amount of total P that was lost as dissolved phosphorus, and we did see higher amounts in our no-till treatments and our cover crop treatment compared to usually our tilled system. Now the broadcast tillage with or broadcast with tillage was actually not statistically different than our no-till cover crop, but we did see the lowest proportion of dissolved phosphorus loss of the total P with our tilled system where we band applied phosphorus. And then if you look at the particulate, that's really the difference, and that kind of makes sense. But one thing that we did reduce in terms of particulate phosphorus loss was if we banded P, even with full tillage, we got relatively lower amounts of P loss there. So this is the phosphorus loss component of this work. When we look at the rates, and now this is including that data plus essentially a meta-analysis we did of all the groups dissolved phosphorus work from 2006 to 2021. And when I finished up there. And what we did was just look at the 3 rates that were applied in a lot of these studies, and they were at 0, 50, and 100 pounds of P2O5. 50-pound rate was generally shooting for about that removal rate of P. And one thing I think that's important is that when we compare where no P was applied to our removal rates, we don't see that big of an increase in P loss. But it's when we're essentially applying that 50 to 100 pound rate, that's where we see that kind of exponential increase in P loss. So maybe you can consider that, interpret that as when we're moving from maybe an annual to a biennial P application method, which certainly is prevalent in use. And there's always kind of muddy points to go through this, right? So previous crop really matters, timing and placement do matter, but when we average these across our rates, these are the general trends that we found. Now this is some older data that was done within the group looking at the relationship between soil test level to P loss in this system. And essentially there was this relationship that, again, it's pretty standard and is usually baked into a lot of state P indices when we're looking at the relationship between soil test and dissolved reactive P loss for surface runoff. But one of the important things to remember is when that agronomic optimum, that agronomic kind of operating space, let's say between 0 and 30 parts per million of Ray P. Now this is a 2-inch depth, so this is a little bit different and stratified when we look at a full 6-inch sample. We don't see, most of this linear trend comes from when we're dealing with high testing soils in an agronomic sense. This is from another study that was done within Northeast Iowa. I wasn't involved in this one, but this was looking at drainage phosphorus concentrations and loads. And again, when we're kind of operating within that optimum agronomic space for soil test P for corn and soybean, we don't see a huge trend. It's kind of a shotgun spread if you look at just these low soil test P values. And so I think this gives us a little bit of confidence when we're kind of playing with agronomic interpretations of soil test P. We're not really affecting what I would say a large proportion of those potentially available phosphorus amounts to be lost. So in summary, I really think what's nice about some of this work and how it all tied together is we've got a system, and again, these are from 2 different states and efforts, but I guess maybe just for me personally, when we're going through and doing agronomic assessments of soil test phosphorus levels, how to interpret them, what does this mean for the agronomic and economic sense of our on-farm decisions, excuse me, we have some consistency with how those ranges perform in our environmental and water quality loss studies. Now, certainly we see some things, flashiness. We know P and within this data, it was certainly present as really event-driven losses happen a lot for soil and phosphorus losses. But if you're in a system that can buffer against changes, I think that's a big benefit. One thing I think that's important is our rotations, especially the soybean part of that, they're flexible in terms of their yield response to different tillage systems, timings, and placements. So we have flexibility to make sure to put that P on when we can reduce losses and have a higher ROI as well. And I think the fourth point is probably the most important to me, kind of a long-term agronomic ROI context and how we manage phosphorus generally does have a positive relationship with environmental outcomes, but we need more data to show this. Sorry, I haven't updated this slide. This is from a talk in Illinois. We need this in Illinois at least to show this work, and that's what we're working on for our nutrient loss reduction strategy as well. And you might hear some more of that from Dr. Margonaut after lunch. But hopefully I haven't kept you too long. I think I'm 20 seconds over right now. But I can answer some questions now, or certainly don't want to keep you from lunch. I can always talk then. I'll be around all day. Thanks for your time. I appreciate it and enjoyed sharing this work with y'all.
First slide, you might see some questions. There you
go. So the first question is, surprised there was not a statistical difference in the corn yields between tillage systems with such a high numerical difference. I believe there should have been a statistical difference between the tillage systems. So our conventional tilled system did yield higher than our no-till systems. The phosphorus placement methods didn't change. So if I shoot back to that slide real quick. So you can see here, although we didn't see these large differences here, so we only saw a difference between the no-till and tilled sites. I understand what they're talking about, around 230 versus 200. The biggest change within these systems were when they were developed and put into place from 2012 to the end of when I worked on them in 20. We actually saw kind of a shift over time in terms of, I would say, yield stability of the tilled system. So again, this study was kind of converted from a manure management study over to a fertilizer management study. And I think that may have been why we see that messiness. So I do agree there does seem to be, when you look at the numbers, there should be a difference, but we didn't see a statistical one, probably due to the annual variability within this data. With increased use of manure, fertility, and cover crops, is there an opportunity for traditional soil phosphorus tests and interpretation improvement? Thinking about how different pea pool sizes or types may be affected depending upon pea extraction procedure use. So the question may be around organic phosphorus and how that may be captured. And I've had some conversations with that within the state of Illinois on what maybe would be advised based off of previous work. I think the challenge is going to be identifying the rate that some of these organic sources of P are going to be available. We can operationally define, if you think of a nutrient cycle, we can define organic P and inorganic P really well through our wet chemistry methods. But the arrows between those, or the fluxes of nutrients, are really tough to manage because it's depending on soil temperature, moisture, the C to N ratio of that manure or residue that's put into place. So I think in terms of traditional soil test methods, it's a little difficult to pull apart what's going to be available for a, let's see, organic P mineralization phase. I think there's maybe some opportunity to look at more biological properties like Jason had talked about. If you can add those on. One thing that I think we've kind of need to realize is that a single soil test value can only do so much. What's the next step of metadata that can adjust that? Whether it's, so we're doing some work in Illinois to look at mapping depth to B horizon in some of our fields and how that affects soil test variability in response to fertility. And there's always a discussion around subsoil supplying amounts of P and K, and Dr. Margonaut might talk about that a little bit later. I think that's something that we can consider. But one of the things that I think is important to hit home about a soil test value is it's not meant to be mechanistic. And the way at least we use these wet chemistry methods, we really need a statistical relationship between relative yield or yield response. So it's not very mechanistic in terms of trying to simulate the plant root. We really need that just empirical and statistical relationship.
Other questions?
Yes, sir.
About when you were talking about your no-till, with the chili farm on that, how many years are we talking no-till? Is it a long-term chili? Would that change the amount of stratification you could have if it's generations or decades of no-till versus 2 or 3 years?
Sure. The question is on so that site, that data is from 2021, excuse me, that data is from 21, 22, 23. It has been a no-till since 2012. And before that, it was yes, sorry. The question was, how long were those no-till sites in place when we were comparing tillage and soil test interpretation across tillage? And does that change in terms of generational stratification? So that site had been no-till for a little over 10 years before we did the comparison between tillage and soil test interpretation. So it certainly was really stratified when we looked at those amounts. I think one of the things that's kind of interesting to do is when we compare exactly where roots are taking up those nutrients, the 6-inch sample depth is generally matching that pretty well, and I think that's probably what we see. And one of the things, again, that I think is important within that context is, you know, there's some data that's talking about whether nutrients cycle faster or slower in tilled systems versus no-till systems, and I don't really have any evidence to show that directly of mine. But I think the most important thing is that we're seeing that, again, it's a response to fertilization as well. And so when we're picking up where the effectiveness of a fertilizer application is kind of baked into that relationship. And so when we're comparing that within our no-tilled systems and whether we see stratification or not, I think there's some role to play in interpreting it that way. A question online, thoughts on how P-fixing soils above 7.4 with lots of calcium might change the conclusions or direction of yield response curves. I would say the first thing that certainly anything with a higher pH or calcareous soils might affect would be the ability of the braid soil test in this case to be able to relate to soil test response, and I think that's why the Olsen test is used as you move west. There's probably something to looking at the occlusion of fresh phosphorus and what's the fate of that fresh phosphorus occluded by calcium over time. I know when we were doing some of the surface runoff work, we looked at trying to develop a calcium impregnated strip instead of an iron impregnated strip to see the role of calcium solubility in P loss. I do think it's important, but I don't know if we have a straight answer on that. I would say in terms of, you know, I don't have as much experience in calcareous soils. I would talk to those in the room that do. But I would say that the probability of response or things that you define in the performance of the soil test maybe won't change, because that specific soil test might as well.
Right, let's get John in here and